For the second part of 4.2, we're going to look at some other notations other than the electron configuration. So these are just some variations. So you would have to know how to write the configuration first before you were able to do these other variations. So the first type is the orbital notation. So orbital notation is going to use a dash to represent how many different orientations we have for each shape. So S's have one, so we would have one dash. P's have three, so we have three dashes. D's have five, so we have 1, 2, 3, 4, 5 dashes, and F's would have 7. Then we're going to use arrows to represent our electrons. So an up arrow would be a positive spin, and a down arrow would be a negative spin. So if this was the original electron configuration, the difference, instead of putting your exponent of 2, you're going to use your dash and your arrows to represent your electrons. So we still have the energy level and the shape. We're just showing the different orientations and the electrons themselves. So for 1s2, we have 1s dash and then our 2 arrows. 2s2, 2p6, all the way to 3p6, and 3d8 would be our last part. So we've got 5 dashes to represent the 5 different Ds, but also remember we have to fill up each orientation, each different dash for D before we can double those up. So when we put those 8 electrons, we would have put 1, 2, 3, 4, 5, and then gone back and doubled up with 6, 7, 8. The next term to know is the highest occupied level. So this just means of your energy levels, which is the highest one that has electrons in it. The inner shell electrons are any electrons that are underneath that are not in that highest level. The next notation is going to be using noble gases. So our noble gases are the group 18 elements, and so we're going to use those as kind of a shortcut to writing our configurations. So if we go back and look at our cheat sheet, the noble gases on that last row basically say if you have a noble gas, everything in that whole period before it is filled up. So that's going to be kind of our little shortcut. So let's say I want to write a configuration for, this is silicon, so it would be, the ending would be 3p2. I'm going to go to the noble gas that's in the row above it. So I go up 1 and all the way over to 2p6, which is neon. That's what I'm going to use as my shortcut. So if we look at cerium, we did cerium in the first part of 4.2. And so this was the whole configuration for cerium. It's rather long. Cerium is located right there on the periodic table, which actually is in this row. So the noble gas, one row up and all the way over, 5p6, is actually going to be xenon, if I'm comparing that to a regular periodic table. Xenon, being 5p6, actually tells us, okay, we've filled up all of these. So if you just tell me xenon, you're taking care of a lot of that. I can also identify which one I'm working with using this chart as well. So if I know that 4F something is what I'm working with, which is here, I'm going to go to the row above and the last one. So once I identify that, or xenon, as my noble gas that I'm using, then I'm going to write xenon in brackets, and then I pick up from there and write everything to the element that I'm working with. And so here's where xenon was. You can kind of see that. So my cerium fit there. We've gone up one row, found xenon. Matches the 5p6. And it says, hey, if you know that xenon, you've already told me all of that's taken care of. So you're going to write xenon in brackets, and this should be a bracket here. And then jump down to your 6s2, and then your 4f with cerium is 4f2. That's all you would have to write for cerium rather than this whole thing here. Now let's try it with bromine. So first we're going to identify where bromine is located. Bromine, the last part, it's going to be 1, 2, 3, 4. It's in the P block, and it's 1, 2, 3, 4, 5 over. The Nobel gas up one and over is argon. So we've got our 4p5, that is bromine. Then we're going to write argon in brackets. Then we're going to come down to the next row. So 4s2. Keep going. Remember, this was 3d10. And now we are at 4p5, and we're done. A couple other things that you can look at a configuration and tell are how many electrons that element has. So if we add up all of the coefficients, or all the exponents, up at the top, that tells me how many electrons something has. So how many electrons do we have for this? So 2 plus 2 plus 6 plus 2 plus 3 is going to give me 15. And I can match 15 up with phosphorus, and that's the atomic number. And since we're dealing with neutral atoms, 15 would be the number of electrons as well. And so that also answers what's the atomic number. So if I've added all of those up, I know it's neutral. That can tell me the atomic number as well.